Hello and welcome. This is a short presentation video for our paper towards a smart highway lighting system based on road occupancy model design and simulation. My name is Ahmed Mustafa and I'm a senior year student at Alexandria University in Egypt, majored in communications and electronics engineering. And firstly, I'd like to apologize because we were not able to attend the conference and be with you, but I hope that through this video we will be able to clarify our idea. So how did we get here? So actually, the idea of this paper evolved when we were searching for wireless sensors networks applications to work on for our academic graduation project, and one of the applications which attracted our attention was using wireless sensors networks for switchable street lighting to adapt with road occupancy, which means that when a road or some sections of a road are unoccupied, lighting will be reduced to save energy. So this idea seemed to be interesting, but we were not sure about its performance and feasibility. So actually some papers, which are mentioned in our paper by the way, tried to introduce some evaluation for this idea through rough calculations or real-time results from implemented systems on small scale, but this information was not enough to show the effectiveness of this idea in different scenarios. Then we thought that simulation would be the best way to evaluate this idea, and in this case simulation has two main advantages. Firstly, it's not logical or even available to implement such large-scale solution to get some real-time data even before feasibility of this solution could be verified. And secondly, simulation gives us the flexibility to predict the performance of our system under different cases and design parameters, as we will see later. And as far as we have searched, we didn't find other works presenting simulations for this idea, so we decided that this would be a good research point to work on. So, in order to simulate our solution, we needed two things: a suitable model to generate realistic traffic flow simulation, and a simple algorithm to abstract the idea of switchable lighting. So firstly, our algorithm is simple. As you can see, the road is divided into sections. Each section is the distance between two consecutive lighting poles, and each lighting pole is equipped with a wireless sensors node to detect cars entering or leaving the section. And each node has a counter, as you can see. So now we are observing this middle section. It's empty and its counter equals 0, and car approaches and it enters the section. So the node responsible for the section, the node on the head of the section, senses the car and the counter is incremented, and another car enters, so counter is incremented again and it's equal to. Now the first car is leaving the section and entering the next section, so the next node senses the car and sends message to the current node, which is the middle section, to decrement the counter, so counter equals 1, and again the next car leaves, so the section is again empty and the lamp N is turned off or dead. And the same process is repeated for all nodes. I would like also to show you a short video for a live demonstration for a prototype which we have built after finishing this paper. Actually, we built it using wireless sensors nodes based on my Arduino microcontroller and ultrasonic sensors for car detection. And as you can see, car is approaching and the first section is on. Then the car leaves it and enters the second section. The second section is on. The first section is turned off. Then the second section is turned off. And after that, as I said before, we need a model to generate traffic flow. So we used the well-known discrete model based on cellular automata introduced by Nagel and Scherkenberg, who are two German mathematicians. And this model can be easily generated and used for computations, as it's a discrete model, which gives it advantage over continuous models, of course. So there are many versions of this model, including different traffic scenarios, including multi-lane roads, for example, but we used the single-lane version for simplicity. And in future, we intend to simulate more complicated traffic cases. And after combining both algorithms, the light switching algorithm and the traffic flow modeling algorithm, we implemented our simulation scenario using MATLAB to predict the performance of our system under different scenarios. And of course, our simulation parameters and simulation setup are mentioned in details in our paper. And our initial simulation scenario showed that our system can save energy up to 57.4% of energy consumption of conventional lighting systems. These results were actually very promising, but we had two main problems. The first problem is that turning off light when a section is empty is a bit risky, because it may affect the safety and the comfort of drivers, which is a big problem actually. And so we suggested a solution for this problem, that we can dim light instead of turning it off. We can dim it to a limit which will not affect the safety and the comfort of drivers. So for example, if you dim light by 50% instead of turning it off, you will have half the rate of energy saving. So in our case, 57.4% of our saving when you turn lights off will be reduced to 28.7% only. The second problem is that our initial simulation showed that each lamp will need to change its state from on to off or dimmed with an average number of 42 times per minute, which means that this solution needs LED lanterns with high response time to be able to deal with these changes. Then we repeated our simulation, changing two parameters. We changed the length of a section, which means that we changed the distance between every two consecutive lighting poles, and this depends on the lighting design of the road. At first we used 30 meters as a section length, and then we increased it to 37.5 meters, which are realistic values. And then we treated each two consecutive lighting poles as one section instead of one lighting pole, which means that we doubled the length of our section. And as expected, when we increase section length, power saving decreases, because a larger section is less likely to be completely empty. But on the other hand, the mean frequency by which lighting pole needs to change its state from on to off or dimmed decreases, which was expected to. And this graph compares between energy consumption in conventional lighting systems and energy consumption in our different scenarios. So to conclude, in this paper we present the idea of a smart highway lighting system which adapts with road occupancy to reduce energy consumption. Our main contribution is providing a methodology to simulate such system and predict its performance, and our simulation results show that this system has good impact on energy saving. Our future work, which we are currently working on, is using the same simulation methodology in other vehicular traffic related solutions. Currently we are using this simulation to develop a predictive model for vehicular cloud computing to overcome the high mobility of the vehicular cloud environment and provide more reliable resources management for vehicular cloud computing. Finally, I would like to thank my co-authors, my colleagues, Omar Abu Bakr, Ahmed Derbala, Assam Ahmed, and finally our supervisor, Dr. Bassem Mukhtar, the assistant professor at the Faculty of Engineering, Alexandria University, Egypt. I would like also to thank the Smart CI Research Center at the Faculty of Engineering in Alexandria University for their support. And this is my email address, and I'll be very glad to hear your comments and questions. Thank you.